with Weka, what has been done with Weka to run chem informatics. I'll describe that, and I'm here over the next 2 days. So this will be a truncated introduction to the entire software. And it's a very how-to. So there's no theory and there's no science behind it. There is how do we, for instance, do data partitioning. Now don't ask me what data partitioning is. That's not the answer you're going to get now. You're going to get, given the set of data, how do you break it up into training and test? Those kind of things. Okay? So tune yourself off science and other things and just get on to the practical aspects. It's going to be a very short talk, only about half an hour. As soon as tea is ready, I'll be kicked out of here. And then you'll have the next session, which will be back to big science. Okay? If you want to, you can make it as much of a dialogue as possible. You can ask questions, but focus on what is happening and how to do something rather than asking me questions on the theory. Okay? Just give me a minute while I set this up. Okay, you can see? Now I'm going to rush through a little bit. Okay, so this is by Max Kuhn, who's part of this particular project. He works at Pfizer. There are 6 of us involved on the OSDD portal in running this project. Max Kuhn leads it. He's from Pfizer. Then there are 2 data mining professors from ISI Calcutta, Sangamitra Bandopandya and Ujjwal Maulik. Then I am working with connecting this particular package with the grid, which is why I'm down over here. And Sundarajan, Dr. Jalil, and the grid aspect, the Garuda aspect, we'll talk about tomorrow. So what is CARET? CARET stands for Classification and Regression Training using the package CARET. I just run through. These are a few references. Okay. Now what is predictive model? Why do we use R? There are a huge number of models. At the last time I counted, there were something like 69 different methods you can use in R. And they come under the following methods. For instance, parametric regression models, sparse models, kernel methods such as SVMs, etc., etc. How many of you know what an SVM is? Well, trees. Do you know what a tree is? Okay, have you had an introduction talk on classification? Yes? You must have, because I've been watching what's happening on this program. Okay, I'll go through again with my original plan of how to, but what we'll have to do is come back into learning a bit of the theory. Otherwise, we'll get stuck again. Okay, so there are trees, there are ensembles. For instance, a modification of a tree that we would use is a random forest. Then there are discriminant analysis, linear methods, and others. Now, the purpose of this slide is to show you that there are a lot of methods. And the question you'd like to ask is, which one do you want to use? Now, in general, the answer is you do not use only one. You use as many of them as possible, which is why we use this package. Now, in the absence of any knowledge about a prediction problem, no model can be said to be uniformly better than any other. And this is the problem that we are working with. We're trying to pick out molecules from PubChem which are antitubercular. How do you know that they are antitubercular? A priori. In the absence of having that information, you can't say that this method is better than some other method, which is why we are going to use multiple methods. And the title of our project is called Ensemble Methods. And we're going to use multiple methods and weight them together. Okay? Now, there are many modeling packages that are written by different people, and there are some problems and inconsistencies on how these models are used. Now, here comes your first problem. Why do you use Weka? Weka has a large number of models, but it has the same interface for all those methods. With R, we have something like 69, 70, 80 different methods. Each one of them is developed by a separate group. Each one of them will have a separate input, a separate output. So you're going to have a problem if you're going to have to use each one of them. You'll have to learn each input and output separately. Okay? So that's what we have. Now, there are multiple methods. Now, to make them into one, there is a consistency of the model function that is used by CARET. So what is CARET? It basically was developed, and there are 4 points there. to create a unified interface for modeling and prediction. It is to streamline the model tuning using resampling. It provides a variety of helper functions and classes for day-to-day model building tasks, and it increases computational efficiency using parallel processing. Now, these are the 4 reasons why we picked up Carrot for a use with chem informatics. So I'm going to repeat them again, and I'm going to explain why. You had 69 or 70 different methods in R. Now, you can't start learning each one individually. Carrot has done that for you. Okay? It provides a unified interface similar to Weka. By the way, Weka is one of the methods that you can also run through Carrot. Now, you use streamlined model tuning using resampling. I'll give you an example, but do you know what KNN stands for? K nearest neighbors. Very good. And what is K? If there are K number of clusters. Now your problem is, what is K? Right? So see, K is something which is a parameter that we need to define. So if you know the number of clusters in the beginning, great. But if you don't know the number of clusters, what you do is you iteratively test with different numbers. So if K is equal to 1, what are my results? If K is equal to 2, what are my results? Now that is called tuning of your parameters. That's the second point. The third is a number of helper functions. How do you know that your discriminator set has highly correlated discriminators, which means that the same discriminator or 2 different discriminators are giving you the same information and therefore are not going to be very different. So you'd like to do correlation studies and other things. There are a number of helper functions that you can pick up. And the most important as far as we are concerned is that when we are doing this real-world research problem, we have a problem that we've got now 25 million, 28 million molecules in PubChem. You cannot work on a PC. You cannot even work with 60 different PCs or 100 different PCs. So we need to be able to work with a system which can scale computationally across high-performance machines. So Carrot does all these. At the bottom are some of the references.